Hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we will continue with the numerical integration. So, in the previous lecture we have introduced that how the rectangular methods can be used for numerical integration. Now, we will continue with that one. So, we take that now, so this is a numerical integration. Now, I have a integral from a to b this function f(x) dx. So, what I do is now we approximate the function that is f(x). So, this function f(x) we approximate this one with Lagrange interpolating polynomial. With Lagrange I know that this Lagrange interpolating polynomial, it can be linear, it can be quadratic, the cubic. So, based on this one we will get the different type of methods. So, I just take the method 1. And we call it trapezoidal rule. So, in this case what we are going to do, that suppose I have a function and some function is given to me. So, this is my x is equal to a and this is the value of x is equal to b. Now, what I do is that I approximate this function. So, this is my function f(x). So, I approximate this function with a linear function, this value. So, this is my Lagrange interpolating polynomial and this is my function f(x). And I am considering that I know the value of the function at this point and this point. So, now in this case we know that if I go back and find the value of Lagrange interpolating polynomial, then I know that I can find this polynomial p1x because I am representing by the linear function. So, this can be written as x minus x1 over x naught minus x1, the value of the function at x naught, plus x minus x0 and x1 minus x0, value of the function at x1. So, I call it this value as x0 and this value I just call it x1. So, I have only two values there. Now, this f(x naught) can be written as y naught also and f(x1) can be written as y1. So, this is the linear interpolating polynomial, Lagrange polynomials for the given function. Now, we know that this polynomial comes with the errors. So, I know that the function, my function f(x) can be written as p1x. So, this is the interpolating polynomial plus the error term. So, that is the remainder term. So, that is Rx, and I know that the Rx in this case will be x minus x0, x minus x1, f second derivative xi over 2 factorial, where xi is lying between x0 to x1. So, this is the corresponding error we can find for this linear interpolating polynomial. Now, from here, now I want to do the integration. So, I am integrating from x0 that is a to x1 that is b f(x) dx. So, this one I am doing. So, I have substituted the value here. So, this is my x0 to x1 p1x dx plus x0 to x1, that is rx dx, and rx is the error term we have introduced. Now, if I want to find this one, so this integration I want to find out. So, first I will find out this integration. So, this integration is x0 to x1 and the p1x is x minus x1 x0 minus x1. So, this is my plus y naught x minus x0 x1 minus x0 y1 dx. So, this integration I want to do. Now, from here you can see that this x0 and x1. So, I can find that x1 minus x0 I represent by h. So, this value. So, now this integration if you want to do, I will get y0 over x naught minus x1. So, I am doing the integration of these. So, it will become x minus x1 whole square by 2 and substituting this integral value plus y1 x1 minus x naught and then it will be x minus x naught whole square by 2 and then substituting x0 x1. So, from here I will get, and this one is the h I have taken. So, it is minus h basically here coming. So, from here I can write y naught over minus h into 2 is there, and now I have substituted the limit here. So, this is x1 is 0 and x naught. So, it will be x naught minus of x naught minus x1 square. I will get this value plus y1 into 2h because this is the h, and then I substitute the values. I will get x1 minus x naught square minus 0. So, I will get this value. So, from here, and this is x naught minus x1 is the minus h, but square is there. So, this minus and this minus will cancel out, and from here I will get y naught into h square 2h plus y1 2h into h square. So, this h will cancel out. So, from here I can write that this as a h y naught plus y1 divided by 2. So, that is the value of the integration we are going to get. And if you see from here in the previous one, now if you look at this one carefully, then you will see that this one is a trapezoid, and if I want to find the area of this trapezoid, so that is the average of the parallel side. So, this will be y0, this is the y0 plus y1, that is the y1 and by 2. So, this is the average of this value multiplied by the distance between them, and distance between them is h. So, that is the area of the trapezoid. So, the same value we are getting here for this one. So, that is same as area of the trapezoid. So, that is why this is called the trapezoidal roll. So, in this case that is the area we are going to get. Now, we want to find out how the error will. So, this error we want to find out. So, this error is x minus x0 dx. So, this one we want to find out. So, if I want to find out from here, then I can, because this is the constant value, I can take this outside and then I can integrate this one. and now this is the product of two functions. So, I can simply do the integration by parts, and if you see this one, I can take this as a first function. So, x minus x 0 and then x minus x 1 whole square by 2 and then minus x 0 to x 1, taking the derivative of this will be just a 1. So, it will be x minus x 1 whole square by 2 dx. So, this is now if I substitute. So, here also we have to substitute the limit. So, if I put x 1, this will be 0, x 0 it will be 0. So, this part will be 0. So, this is equal to 0. Now, from here I will left with this value. So, from here you can say that we have f double dash xi over 2, and then I will do the integration. This xi, I know that this xi belongs to x 0 to x 1. So, this negative sign, and I will take the integration of this part. So, this will be cube by 6. So, it will be 6 there, right. So, from here this will be minus. So, this I can write minus x 1 cube by 6 and then putting x 0 and x 1. So, when I put the value x 1 here, it will be 0 and x 0 will be h with the negative sign. So, from, and this will be 12. So, I can write this one minus f double dash xi over 12, and this is 0 minus x 0 minus x 1 cube. So, this is the integration. Now, x 0 minus x 1 is minus h. So, this is the minus h by cube. So, minus sign will come out. So, from here I can write this is equal to minus f double dash xi into h cube. So, I get this value. So, from here I can write that the error term in this integration will be h cube by 12 f double dash xi, and where xi is lying between x 0 to x 1. So, that is the error in this integration. Now, from here you can see that this error is the second order, second derivative of the function f x. So, I can say that for linear function f second derivative is equal to 0, which implies that this method gives exact solution for linear function. So, for the linear function, if we are doing the integration, then we will get the exact value of using the trapezoidal rule. So, that is the way we can find out the error. Now, this is we have done now. Now, what is happening in this case? In the previous, if you see that the whole function I am approximating with a linear interpolating polynomial, and we are able to find the solution. But if you see from here, the error is quite large. So, this is the error we have introduced. This is the error, this is the error. So, the error is very large in this case. Now, what do you do that instead of this one, what we can do, we can split the function into n plus 1 nodal values as we are doing, and this is my x n is equal to b, this is my x 0 is equal to a, this is x1, x2, x3 and so on. Now, what we can do that this function in the first subinterval, I will approximate this one with a Lagrangian interpolating polynomial, and then so this is the first trapezoidal I am going to get, and then I will find out this value. Next one is that this function, the next is this function, and this value I can this and so on. So, based on this one I can, for my integration from a to b, my fx dx, I can split this function, the whole integral in this form from x0 to x1. So, this the area of this one. So, I can write this value, this area. So, then I can write this fx dx plus x1 to x2 fx dx xn minus 1 into xn fx dx. So, I split the function into all this subinterval, and now this one can be separately solved as we have done in the previous one using the Lagrangian interpolating polynomial. Similarly for this one, and so on. So, if you see from here, then if I find the value of this integral with the trapezoidal rule, then I will get the value here. So, what is the area of this trapezoidal? I will get the average of this value. This is the y0 and this is my y1, and then distance between these two. So, from here I can write that using the trapezoidal rule, the area of this trapezoid will be h. So, h I am taking now. So, my h is b minus a by n. So, n is the number of subinterval I am finding. So, this is my h basically, this is the h. So, from here I will get y0 plus y1 by 2. The next one I want to find out this value. So, this will be again plus h y1 plus y2 by 2 and so on. The last I will get h y I n minus 1 plus y n by 2. So, this is the composite form we are getting. So, from here the composite formula for the trapezoidal rule is, so from here if I add all together, then my integration from fx dx, that becomes, now if you see from here, h and h is coming common, 2 is also coming common from all these values. So, I can write from here h by 2 and then y0 is coming, but if you see from here y1 is also coming here and coming here. So, this is the connecting node. So, this values which are connected by 2 subinterval, so they are called nodes. So, this is the connecting nodes. So, in this case the connecting node is y1. So, I will get 2 y1 plus y2 plus y3 up to yn minus 1 plus yn. So, this value I am going to get because yn minus 1 is coming. So, this is the value of the connecting node yn minus 1. So, it will be used in the left side also and the right side also. Okay. So, that is the formula of the composite for trapezoidal rule. And what about the error in this case? So, of course, the error will be added. So, from here I can write the total error. So, the total error TE. So, how I can find the total error? I can add this one. So, this one I can write that the upper bound for the error in the composite formula may be taken as n times the largest error in any subinterval. So, if you see from here, I can write then the total error will be minus n times. So, this is n times I am writing, otherwise it is, I know that this is equal to h cube by 12 f dash double dash xi, where n is equal to, so this is, so h will be b minus a by n. Okay, so from here I can write this one. So, this is the total error, where xi I am choosing that this value is the largest error. So, I will find out the largest error in any sub interval and then I multiply by n. So, that is the truncation error we are going to. So, this is the upper bound for that one. So, truncation error we are going to get in the composite formula. So, that is the way we can find out the error in the composite formula. Now, so this is the simplest one we have taken. Now, the next method we are going to introduce is, because in this case we are approximating the given function with a linear Lagrangian interpolating polynomial, but we can go further. And how we can go further? Now, suppose I have this function, so I know the value of the function at x0 and maybe x1. I just take it x2. So, this is my a and this is my b. Now, I choose a in between point. So, that is my, I call it x1. So, x1 is a plus b by 2. Now, in this case, this is my function f(x). So, I can approximate this function with a quadratic polynomial, interpolating polynomial. So, what is the quadratic interpolating polynomial? That it is passing, it is a quadratic and passing through the points. So, this is my, I call it p2x. Now, this is the quadratic interpolating polynomial. So, now we are approximating our function with p2x and some error will be introduced, and then what we do, then we will solve this one and we will find out the integration under this p2. So, that is the way we can define. So, this is the method 2 and this is called the Simpson rule. Simpson rule. So, in this case what we are going to start with, we have a function. So, this is my integration I want to find out. Now, we approximate the function f(x). So, f(x) I approximate with p2x plus the error term or the remainder. Error we call it a remainder term plus Rx. Now, what is my p2? So, p2 is the polynomial, second degree polynomial, that is we call it p2. So, in this case it will be x, so x0 is there, so it will be x1 x minus x2 divided by x0 minus x1 x0 minus x2 y0, the value of the function here. So, this is my point x0 y0, this is my point x1 y1, and this is the point x2 y2 plus x minus x0 x minus x2, and that will be x1 minus x0 and x1 minus x2 y1 plus x minus x0 x minus x1 x2 minus x0 and x2 minus x1. And that is y2, and the error terms Rx is the remaining term. So, I know that this will be equal to x minus x0 x minus x1 x minus x2 f third derivative by 3 factorial, and where xi is buying between x0 to x2. So, this is the corresponding error in the approximating the function with the second degree Lagrangian interpolating polynomial. So, from here now we have to introduce this one. So, from here I want to find the integration, that is x0 to x2, that is b, my fx dx. So, this can be written as x naught is equal to a to b, that is x2, my p2x dx plus x naught to x2 rx dx. So, this integration we have to find out. Now, the question is that how we can integrate this one. So, in this case we are going to start the integration. So, now I need to find the integration from x0 to x2 x minus x1 x minus x2 x naught minus x1 and x naught minus x2 y naught plus x minus x naught x1 minus x naught and x1 minus x2 y1 plus x2 dx. So, this one we need to find. So, let us do the integration for this. Now, we know that our so the first integration I want to solve. So, let us solve this part first. So, in this case, so let us start this one. So, now I want to find out this x0 to x2, and this part I can take outside because this is a constant value. So, x0 minus x1 and x0 minus x2. So, this part I can take common, no problem. Inside I will get, and y naught also I can take common, y naught. Now, this is x minus x1 dx. So, this one value I want to find out. So, now I will, the one thing is that we can do the integration directly, but then it will sometimes it becomes cumbersome to this one. Now, just take the transformation. Now, I know that my value x can be written as x naught plus ph. This is we have done for the when we are doing the interpolating polynomial, that we can represent the x is equal to x naught plus ph, where p this parameter we introduce it generally it lying between 0 and 1. So, from here I can write my x minus x0 becomes ph. Now, from here if I put x minus x1, then this will be x naught plus ph minus x1. This one I can write. So, from here I can write x naught minus x1 plus ph, right. Now, I know that x naught minus x1. So, if you see from the previous one, I can say that this is equal to h and this is also equal to h, the distance between x1 and x naught and x2 minus x1. So, from here I can write that this is minus h plus ph. So, that can be written as h I take common, this becomes p minus 1. Similarly, x minus x2 can be written as x naught plus ph minus x2. So, again I can take this x2 x0 minus x2 plus ph. So, this is x2 and x2 minus this is minus 2h plus ph, and from here I can take h, this is p minus 2. Now, from here if you, then also that if you write dx, so it will be h dp, and when x is equal to x naught, p is 0. So, at x is equal to x naught, p is 0, x is equal to x2, p will be 2, because x is equal to x2, so it will be 2h, so p will be 2. So, from here I can that this integration can be written as y0. Okay. So, this x naught minus x1, x naught minus x2, and this can be written as 0 to 2, x minus x1 is h p minus 1 into h p minus 2, and dx becomes h dp. So, h dp. So, this integration becomes this one. So, from here I can write this h and this h, I can take common h cube y naught over x naught minus x1, x naught minus x2 and 0 to 2. So, this becomes, it becomes p minus 1 into p minus 2 dp. So, this is the integration we need to find out. Similarly, we can define for integration for this and this. So, we will stop here. So, in this lecture we have started with the method that is called the trapezoidal rule, and then we have started with the Simpson rule. So, in the next class we will carry out with the Simpson rule. Thanks for watching, thanks very much.